7-1, because the central limit stuff wasn't on the last test. Ooh, neato. Hidden parabola. So we've got, you've got this guy. If you don't know this guy by now, just don't tell me, because I'll cry a lot. That won't be nice to see. And this is what chapter 7, remember, this is the big thing from chapter 7 was, if I take a sample and I plot the sample means, the standard deviation is going to get smaller. Because any sample I pick, its mean should be close to the real mean. So that's the central idea behind that. So that's chapter 7, yeah. Okay. If you want to, you can put this down here also, but you can bring your old formula sheets in too. Okay. Then chapter 8 is where we got into confidence intervals. So there's 5 main formulas from there. There are these 2 here. Can somebody remind me how do these act like a note?
If it's a sample, you use T. If it's a population, you use Z.
Yeah, population standard deviation, Z, sample standard deviation, that's why T's were invented. They're a little bigger than Z-scores to help cover my ass or something I don't know. Yes?
Are we allowed to make note what chapter when you got these points?
I mean,
it just helps me sort it.
And that's why I'm sorting them. Yeah, let's stay away from any like that. And then there's this one for percentages. And the big clue there is there's only one formula for percentages, so you never use t-scores with NPQ kind of stuff. That leads over into hypothesis tests too. We saw that the other day. You just never, T's weren't invented for percentages. They were invented for means. Okay. All right. I love how some of you still have no idea what to make of me. I love it. Then there's 2 N formulas. When do you use these formulas? Whenever I feel like it. What's that mean? Number in your sample. So this is when I ask you how many people do you need in your sample to be within so much or some word related to within, right? So of course, I teach the derivation, you teach where things come from, you teach the ideas behind things. But when you come down to it, you use the formulas that make sense for what you're given or what you're asked. I'm not going to use this formula if I'm talking about percentages. There's no freaking percentages in there. So you kind of can limit, if you're not sure what to use, you go, well, there's percentages. It's only got to be something that has percentages in it that'll help you pick the right formula, right? Yes?
The bottom one, is that Z squared, P hat, Q hat?
Yes. And again, if you're just making a formula sheet from writing what I'm writing and not double checking it later, you're a little insane. You should probably check these to make sure you wrote them down correctly. All right, so that's chapter 7, chapter 8. And then chapter 9, of course, is our favorite so far. The hypothesis tests. Oh, they're so awesome. I don't blame you. Okay. And the only real new thing from that chapter really was this guy. Right? I mean, everything else is kind of old, but just reorganized. All right, so does anybody think there's a formula I've left off that you should include yet?
I can't really recall right now, but S equals the one that you should do to find S.
Oh, do you mean like the, all right, I mean, It's the same formula as this. S x bar equals S over the square root of n, that one?
Yeah.
Sure.
Sorry.
Yeah, whatever standard deviation you have, if you take samples, you got to change it from the one that works for individuals to the one that works for groups.
What about the one with error?
I mean, I don't mind if you do this, but, you know, for example, right, if you want to write down each of the error that's there, that's the error for that, that's the error for that. And of course, these are using the errors, right? Is that what you're talking about? Anything else you think should be on there? Examples, no. Huh? Oh, I already said no, so hot here. Yeah, be late to the party. Anything else? Okay, alright, so that's it. So you guys can bring this, you can add it to old formula sheets, you can make it its own formula sheet, bring all your formula sheets with you. I don't care. Again, if you lost points on one from before, maybe rewrite that. Don't lose those save points again. That would suck. Okay. So now it's wide open to whatever you just want to do some problems. You want to. Is everybody going to do chapter 10 that I made extra credit? If you're going to do chapter 10, you could put the formulas from chapter 10 on your formula sheet. All right. You're probably going to have a bonus question from chapter 10. And just to show you guys, if you don't want to write this down, you don't need to. I just want to show you. Obviously, I always want this to make sense. But, so for example, here, you know, I've got my data minus the middle divided by the standard deviation. And I change this if I take a sample. So when I do this step in the hypothesis test, I'm going to divide by the new standard deviation, right? It's always a part of the process. But I'm comparing my sample mean to some given mean. So in chapter 10, what you're doing is you're comparing two sample means. So if I gave a drug to a sample of men and I gave a drug to a sample of women, and I wanted to see how different are those two samples, there's no given mean. There's no mu. There's only a couple of x bars. There's x bar 1 and x bar 2 for the two different samples. Are you guys semi with me? And again, chapter 10 is extra credit, but chapter 10 is all the exact same 5 steps. It's the exact same freaking 5 steps. It's just that I need a bigger formula than before, right? So the formula, officially, if you want to write this down, you can, is this guy, right? That's the formula we use on that 4th step in a hypothesis test for a mean. For chapter 10, if you're not going to do chapter 10, you don't have to write this down. I just want to show it to you. Instead of x bar minus the mu, it would be x bar 1 minus x bar 2 to see how far apart those two are. The bottom is going to have to get bigger too, because now I got to have 2 standard deviations, because I have a standard deviation for each sample. So it's a little more than I wanted to do, but it's still good for you to see. This here, right? You guys know this. And we know this. Now watch. Stay with me now. It's kind of nifty. Isn't this the same thing? What square root of what is s squared? Is s. Square root of s squared. Good job. So this is the same thing here. These are the same thing. Because what's the square root of s squared? S. What's the square root of n? Square root of n. These are the same. And now I just put 2 of them in there, because I'm going to have S1 for this first sample, S2 for the second sample. So I said earlier this semester the formula for the z-score never changes, and I still stand by that. I don't care how crazy you think I am. So there's 2 sample means instead of 1. There's 2 standard deviations instead of 1, because I'm dealing with 2 samples. That's chapter 10. And again, if you're not going to do chapter 10, don't even write that down. You'll just freak yourself out when you're taking the test. Like, oh my God, I was supposed to use it. No. So there will be a bonus problem related to that. Okay. I like it. Yeah.
So that's one whole thing. It's like x bar 1 minus x bar 2 divided by.
Yes, this is the Z-star formula for that fourth step. How far away do we get? It's actually how far apart are my two samples. Yeah. If they're really far apart, that's evidence that they're not equal, right? So, like if I gave a drug to men and a drug to women, what am I trying to show evidence against? That they affect men and women the same. So, if the effects are so different, if the z-score that relates to their difference is really big, how big? Well, it depends on alpha. Then that's evidence that they are different, that the population means are different. Yes?
Are we going to learn about chapter 10 after the test?
I can talk about it a little bit, but...
So, are we still going to be doing the homework then for chapter 10?
So again, chapter 10 is... That's correct.
Oh, even homework.
Yes. I mean, that's... Yeah. Okay. Alright, so now it's wide open. If you want to look at a problem on the practice test. I just want to remind you guys, like number 3. There, I'm going to put a problem like number 3, not necessarily exactly the same setup, but a problem where I give you a list of data. So then you have to calculate your own mean, your own standard deviation. And how do you do that now that we're past the first test? You just do what? How do you calculate the mean and the standard deviation real quick?
1 bar.
Yes, put them in list 1, do 1 bar stats. It was only the first test that I forced you to do the standard deviation table by hand. Right? And you're like, oh, this guy, I know the buttons will do it for me. I don't care.
So you put the pattern, or you put them in different columns.
Oh, so if I give you, like, here's 2 sets of data. When I did this problem, I did L1, and I did 1 var stats on L1, and then I put the failed the class in L2, and I did 1 var stats on L2. Cool. Yeah.
Can you do the problem that relates to that formula?
Oh, to one of these?
Yeah.
So let's see, there's 2 of them. There's 1B and 2B. So I mean, I've done both. But on the answer key, but we can look at them real quick right now. Does everybody got what they want from this here? More than you ever wanted? Okay. So, for example, let me do this. We've already got those on there. I'm going to give you the answer key. So what about this? What if I say, make one little change here. I don't like. Make this 11.9. Then 11.98. So how many people need to be surveyed? Like, that sounds like some horrible cooking thing, Jeff. Surveyed. Surveyed. To be within 3, blah, 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 blah. So you guys, again, I take you through the derivation, I take you through why a formula exists, I take you through where it comes from, what the idea is. But now, as a student, you're going to go, That's a huge clue as to what the hell. Plus, you know what I was just asked to do. But how many people, okay, that's n. I probably want a formula that's solved for n. I mean, that's kind of the logic now that we have these formulas set. Sigma is 11.98, so we're talking about a mean, right? This would be like part B of a problem where I'm talking about make a confidence interval for the mean. So what is 3, for example? What the hell is that?
Error.
Error. So E is 3. Sigma is 11.98. What does 99% confidence tell me?
The Z-score.
Z-score?
2.22.
Nope.
2.575.
Yeah, 2576. Let's use the T-score chart. Gotta be careful. If you look up 0.99, you're not. I really want this to make sense. Now watch. If you look up 0.99 on the Z-score chart, you'll get the Z-score with 99% below it. Okay, stay with me now. Stay with me. This is the kind of number crunching you've got to be able to do at this level. What's this? 1%. So if I cut this off, isn't this 1%? So isn't this really the Z-score for a 98% confidence interval then? 2.33 is for a 98% confidence interval. If you look up 0.99 in the Z-score chart, it ain't going to give you the right thing. Because I don't want 99% all below it. I want 90% in the middle of two Z-scores. That's how I make a confidence interval. Right? So where's the better place to look? The T-score chart. 99% confidence, I want 1% in two tails. That's the first column. Go all the way to the bottom. 2.576.
So if we don't have like error, what is that called? Like the n-1 and it's all the way to the bottom.
Yeah. If I want a Z-score, I go to the bottom. If I stop, I get a T-score. So again, if I want an 80% confidence interval, that means that 80% is between two Z-scores. If I look up 0.8 on the Z-score chart, I will not get what I need, because I'm going to find a Z-score that has 80% completely below it. This Z-score, how much, the right Z-score, that's the right Z-score, right? How much area is actually below this? Anybody figure that out? How much total area is below that Z-score?
80%.
Say again?
No.
It's not 80 because it's not including this, is it? How much is this? 10, isn't it? 10. So how much total area is below that? 0.90. Oh, yeah, see, that's something you should be able to do. So the right Z-score would have, this Z-score doesn't have 80% below it, it has 80% down to the next one, right? How much area is actually below the Z-score? 0.9. If you look up 0.9 in the Z-score chart, you'll get 1.28, which is the correct Z-score for that. If you look up 0.8, you ain't going to get the right one. It just ain't going to happen. You're going to get a Z-score that's too low, because I have to push it down a little bit so it actually has 80% below it. If you can't understand all that, it's a bad sign. I'm just be honest. You have to understand the difference between confidence interval Z-scores and the Z-scores you get from the chart. The chart's always all the way down. And what do confidence intervals do? Chop the middle. They're not going to be related, are they? No, of course not.
No, that wasn't my question.
Okay.
My question was, normally, like you said, original one, 99%, wouldn't it be 0.5 on each side? Like we
Yeah, so 0.005. Sure. And then you can look that up in the Z-score chart.
Okay, because I was hearing 1. I thought we were looking at 1.
Well, if I'm using a T-score chart, I can look up 0.01 in two tails,
Yeah.
which is the same thing as 0.5 in one tail. Or 0.005, yeah. All right. Okay, maybe. Yes?
It's kind of like on the practice test on 1D. Like I get what you did there, but how would you set it up with like within half an hour? Like,
Well,
what would you do for that?
so what's the error then?
Maybe half an hour.
Yep,
Half-
0.5.
Just 0.5?
Sure.
Oh,
You could put a half in there too. The math doesn't give a crap, but to make sure we put it in the calculator correctly, you should probably make it 0.5, so it's a single line. I got you. Otherwise, you might put it in wrong with that fraction inside of a fraction. That's really weird with Russian nesting fractions. I like that joke. It's my first joke. So, all right. So, where do you want to go now? Oh, well, okay, you could. What else do you want to talk about? You want to do some examples?
So,
Yes.
question number 3. We have to find the mean and standard deviation on both.
Now, what do you think is going to happen in number 3? Number 3 is asking you to make 2 separate confidence intervals for 2 separate groups. What would be evidence that the means are different if I get 2 confidence intervals that don't do something? So a confidence interval is kind of like, it's not this exactly, but it's kind of like a min and a max on the mean, what we think the mean might be, in a really rough way. So this is why we don't use them as proof of something. We use hypothesis tests to test a claim, but you can still get a rough feel for things with the confidence interval, and confidence intervals are quicker than freaking 5-step hypothesis tests. So if I make 2 confidence intervals, so like for example, if I said one confidence interval said it was somewhere from 5 to 8, and another one said it was somewhere from 7 to 10, is it possible that the mean is the same between these two? Yeah, because this could be up to 8, this could be down to 7, so it could be the same. Now, if this was 9, from what we see, do we think they could be the same? No. There's a definite difference. But there's always a chance that I'm wrong. So the 95% confidence, there's a 5% chance I'm wrong. Which is awesome. That's so real life. Math is always acting like it's got all the answers. Stats is like, oh shit, not always. I'm only this sure about it.
Did you already pass out the answer sheet?
Nope. I never do that right away. Just to try to trick you into staying and actually learning some more stuff. I am constantly tricking students into doing the right thing for themselves. And sometimes people can't be tricked and they fail, and I don't know what to do for them. Yeah?
Can you do an example from chapter 9? Just like, it doesn't have to be one of the tests. Just anything.
All right.
Preferably something that would be on the test.
Well, something like you just not the one that's already have
Exactly, yeah. I got you. Preferably the exact one that's on the test. I don't even know what's going to be on the test, so no. So let's say we feel that Jeff's average grades have decreased over time. Right? Let's say like 5 years ago they were the mean was 79.2, and now we take a sample of 91 grades and find a mean of 77.1 with a standard deviation of 11.927. Woo! So roughly based on the truth. So conduct the test with use alpha equal to point, which got you, say 0.5. Okay. This is the kind of problem we've been doing so many times. You're all like, good Lord, let us stop. But you got to do several examples until you really get a feel for how everything goes together and works. You just have to. Where do you start? What's the very first thing you look for? You don't care about anything else at first except one thing, the claim. So What claim is being made?
Decrease.
All right. Average grades have decreased over time, so they're decreased from what they used to be. So write that in. What's that in mathish?
7.92 is less
No.
than, or
Nope.
Is it like,
What do we think about the mean now? We think the mean, as it is now, mu, whatever that mean is, we think it is less than 79.2. What number would never show up in the hypotheses?
that one.
That one, because you set your hypotheses up before you even go take a sample in the real world, right? You have to have a feeling of something. I think it's this, and then you go take a sample. So I feel like the mean is gone down from here. I like it. So just to make sure there's nobody kind of left wondering about this and just not telling this to me. Why can't I just stop right now? That is less than that. Shit, Jeff. All you math people making everything so freaking hard. That is less than that. Stop it. Why is that not good enough? Why is that not good enough? That is less than that, but why is that not good enough?
Because the mean might not be right.
Why not?
you need evidence.
True, but that's pretty good evidence to me.
Because it's the same.
It's only a sample. It's only a sample, right? And a sample, while it should be close to the real mean, there's no way to tell. I gotta check to see if it's random noise. Is that less than this just because of a chance that I just happened to pick 91 grades that were low? That's kind of what this test does. It compares what I see with the possibility that it's just random variation in my data. So which one is this? The low or the high? Totally. I like it because it's missing the equal sign. This is the one that's going to set up the rejection region. It's one of the, I think it's somewhere else. In this case, I think it's there, right? So this one is going to be what? Greater equal than. So now for 2, so it's going to be a one-tailed test down there because I need to show that the mean is down far enough. I like it. Which is why the t-score chart is set up beautifully with the 1 or 2 tail option. One tail. Z or T? Zort. Zort? Why T? All right, one thing you can tell me is sigma unknown. Sure. But then there's the second thing. Well, that's the same thing. I like that. Sigma's unknown. S is known. Okay, you just told me the same thing twice. We got to know some kind of standard deviation. If any sigma is S. What's the second thing you got to tell me? It really should be the first thing you tell me. Because it's what tells you if you do anything in it at all. Yeah, and, no, careful. N is 91, which is greater than 30. N, P, N, Q were the percentages. The 5 is the magic number. Alright. So I use t-scores because it is normal, but I don't know the population standard. I got to use t-scores. So now that I know what I need to use, it makes sense that the next step is going to go ahead and go use that. Right? That's why step 2 is where it is. So I know my place is down there. What's the degrees of freedom? 90. And what's alpha? 105. Cool. And it's a one-tailed test. So can you find the t-score for that? Ooh, I got a t-score chart. So your region of freedom 90, 0.05 and one tail. So you should be looking at this column, stop at 90, and what do you see? 1.662. I heard somebody and I heard somebody else with the wrong. So what will it be? Is this cool?
Negative.
It's got to be negative. How do you know it's negative?
Because it's on the left side.
Yeah, it's below 0. I mean, so don't screw yourself over by setting up your evidence. What's the meaning of evidence wrong? If you have a positive one there, you're going to mess yourself up later, possibly. So if in this case T star, I guess you call it, is My toe. Oh my God. I remember my sister went through that phase. Oh my God. Just turn blue and die. So if T star is, gonna bring that back, less than negative 1662, what can we do? Reject the hoe, support the high. Okay, cool. Let me put the fourth step over here since all the stuff we need is here anyway. So now that I've set up what enough evidence is going to be, then I immediately go see how much evidence that I gather. How far is the sample away? So every step kind of leads into the next step, logically. So what do I know from my sample? X bar 77.1. N was 91. Standard S shows 11.927. And before I figure out T star, what do I need to do? What do I always do in this step with this? Find the new standard deviation. This is the one that works for individuals. In my sample, I need the one that works for groups of 91. So S X bar is 11.927 divided by square root 91. So whatever that is. 1.3. 1.250. Oh. All right, I'm with you. That's pretty good. That's pretty close. And by the way, this is sort of the bane, a little part of the bane of my existence, but if you want to, if it makes you feel better, you can go back to your formula sheet. I don't know if anybody's all freaking out about this is T star. I don't know if you remember I told you Z star, T star, they're the same damn thing. But if you want to put the formula down and pretend like it's something new, you can. So the formula is this. Oh my God, we have an S there instead of sigma. S goes with T, sigma goes with Z. So you can put this on your formula sheet if you want to. It's the same formula, really. I want to see how far my sample got from my mean, the mean from the claim, in standard deviation. So that's how I measure distance. So what do I put? Let's see, what goes here? 77.1 minus 79.2. Where would this number always come from? It always comes from the claim. That's the number you're trying to see how far away you got from, to try to show that it isn't that. So that's always going to, whatever the number is in the claim, as long as you pick that number correctly, that's going to be what goes there. And then I got on the bottom 1.25 for it. 7 force is like 1.75. Probably take that too fast. 1 point, well, it's going to be a little less than that, so 1.7. Negative.
Negative 1.68.
Yeah. Got to show off somewhere. Can't do it on the basketball court exactly. Watch basketball really well. Oh, this is so freaking cool. Holy shit. All right, I wish I could take credit for making it this close. You guys see what I'm talking about? Do we make it far enough? We had to get at least this far away, and we got a little bit further away. Yeah. We got like right here. So it doesn't matter that we just barely passed. We passed the test. We found evidence. So what does this mean? What's my little phrase I can write to help me with the last step? We can do what now?
Fail to reject the vote.
Don't go all there. We can Wait, what happened? Did we fail or succeed?
Succeeded.
Because we got into the rejection region. That's where we're trying to get to show evidence. Now, sometimes we don't want to show evidence that it's wrong. Sometimes the hoe is what we are claiming. So sometimes we don't want it. But the test itself, to succeed, it's got to get into the rejection region. That's far enough away. That's evidence. So we totally succeeded. So we can reject the null, support the high. Because we made it into the rejection region, we can reject. That's crazy. That's why I call it. I think the book calls it the critical region. Rejection region just makes more sense. So let's see. I got a different color maybe this way. So the last step now we can do. What was my claim? Which one was my claim? The high. So I want to use this language. There's nothing more to it than that. There's no guess, please dear God, let it be this word that I'm supposed to use. No, it's just use the one that's related to the claim. So we have found sufficient evidence to support the claim. Don't say hi in there now. Support the claim that what? That Jeff's. Is that the one we're doing? So Jeff's average grade. I guess Jeff's student's average grade. I'm not taking any classes right now. Just barely. So if I would have made this, now here's another question I sometimes ask. What if alpha had been 0.01? What would have changed? Yeah. Can anybody tell me what it would have become if alpha had been 0.01? All I got to do is go back to this and then go over
1.291.
No.
Oh, it's
2.368.
Yeah, so 0.01, 2.368. Would we have made it far enough? So it would be negative 2.368? Would that have been far enough what we got? No. That's why it's called the level of significance. The smaller this is that we pass, the more significant it is what we found. So that's why I said for trying to prove that you should be able to pay less insurance, they're going to make this number small to make it hard to pass that test of evidence, right? Because they want your money. Or again, if I'm in a nuclear power plant and I'm calculating this based on the readings, I'm going to make this big. Because I want to get going the minute something is anywhere near unusual, right? So I'm going to make this big so I'll get off my butt more, quicker. Go run and see, Godzilla's coming, holy shit. Brian Cranston, yes?
So say it was a Z-score, would we have P's and Q's instead of S's and X's?
The only thing I'd have to change to make this a Z-score would have been the standard deviation would have been the population standard deviation. Right? If this would have been sigma here, you with me?
But how does that apply to the formula if there's only P's and Q's and
Well, that's a percentage problem formula, and I'm not talking about percentages here, right? I'm talking about averages, so means. Yeah, do you see what I'm saying? So I wouldn't use P hat and P and all that kind of Q, unless I'm talking about percentages of people that do something, right? This is the mean grades, the standard deviations. That's going to be not a P hat, Q hat, whatever. Yeah.
Can we do a percentage one?
Sure.
How do you find the P value?
Oh, this one, it's going to be hard because this is a T-score. I really want this. You guys understand how this is nowhere near as detailed as the Z-score chart? To be as detailed as it, for every degree of freedom, it would have to have its own chart like the Z-score chart. to be as detailed. But let me see if I can get you guys to go with me for a second. We got 1.68, right? And the degrees of freedom was 90. So where's 1.68? It's in between what two on the 90, at the 90 level here? Where's 1.68 between which two? So at 90, where's 1.68 between what two t-scores? Yeah, and 1.662. So the p-value would be between, this is one tail, 0.025 and 0.05. That's the most we could do because the t-score chart is nowhere near as detailed. So all I could do for the t-score p-value is to give a range.
Okay. So let's say we're using a z-score chart.
Alright, so as we're using z-scores, let's pretend like this was a z-star, right? You would just look up negative 1.68 and get the area. And then that's your p-value. Two-tail, you gotta double it. Hopefully that makes sense. So the alpha, where's alpha on this picture? Where's alpha on this picture? Where's alpha?
105.
No, where is it? The shading. That's shading right there, right? So the p-value would be the shading in this tail. So, yes?
So if we use the z-score chart, it would be 0.9535?
No, negative 1.68.
Oh.
Yeah. Even if it was positive 1.68, the tail would be up there. I'd have to do 1 minus to get the area up there, right?
0.0465.
Sure. Okay. So I don't know if you understand what I just said was, I'm not going to ask you for a p-value when I have t-scores for you, right? Because we didn't really cover that until just now, and that was for like 10 seconds. So I'm not going to count that as a lecture on t-score, p-value stuff. Cool. So z-score problems, I'm definitely going to ask you for a p-value. Because that's what you put in journal articles. That's what you have to understand when you do a study. That's what you want to report to people. And then they can make up their own mind. So this alpha here, is different for different people. I don't know if you understand. So if I get a p of 0.03, all right, here we go. You ready? This could be related to a question I asked you on the test. All right. It's true, by the way, but I like to say that because then people pay more attention. 0.03 p-value. Is that good? Is that evidence? Would you say it's evidence?
No.
What would be evidence for you? Would it be evidence here? Yeah. It's less than that. Right? So it depends on what alpha is, but alpha isn't some thing that came from aliens on Mars. It's like your alpha. No. It's every person or every group that's associated with the problem would have their own alpha. That's why they only report the p-values. Then I can make up my own mind. So if p is 0.03 and you're like, well, I require 0.01. And then somebody else is like, no, 0.05 is cool with me. Then the findings was evidence for this guy, but it wasn't evidence for this other person. Which again makes sense. It's because there's uncertainty. Why is there uncertainty? Because we're alive. And there's uncertainty, period. Shit. So that's why people can make up their own minds. That's why they report p-values in those journal articles, because then you can make up your own mind. What's a level that would work for you? What's evidence for you? Yeah.
There's something in the homework that says about critical value.
And I forgot. Did somebody ask me a question about... Oh, somebody wants to do a P. We'll do a P, and then what else did you ask?
I was just curious what critical value
Oh. This is the critical value.
Oh,
So the book calls this the critical region, and this z-score, they call the critical z-score, the critical value.
Oh, okay.
Yeah.
So this is this one.
Yeah, is that z-score? And then I can't remember, this book calls it the test statistic. Is that sound familiar now? Okay. And that's what sometimes they call the z-star or the t-star. They call it the test statistic. But apparently maybe not, or people just aren't reading the book. Okay.
And the homework maybe it's student.
No, the T distribution is called the student's T distribution. Because the guy turned it in an anonymous name, he just called himself student. The guy that worked at the Guinness Brewery. It's like judicial system. Makes you sound drunk. Yeah. Oh, what are you gonna call this building? It's called a bruh. All right, let's leave that behind. I liked it, but it has nothing to do with this shit. So let's do a hypothesis test with percentages. Again, all the steps are going to be the same. The two places that are different are what am I going to have to do on this step for percentages? I have to check what?
It's
NP, NQ, greater than 5. And then what's going to change on this step? I'm going to have to use P hat minus P over the square root of PQ over N. It's got its own z-score formula because it's got its own spread and all that kind of stuff. Right? Okay, so let's try it out. Oh my God. Is this guy still going?